And welcome back to our cosmic journey. We are, of course, now shifting gears to explore the outer planets of our solar system. So, when we talk about the outer planets, we, of course, are referring to the giant planets that inhabit our solar system. The four giants in our solar system all have hydrogen atmospheres, but the warm gas giants, Jupiter and Saturn, have tan, beige, red, and white clouds that are thought to be composed of ammonia ice particles with various colorings called chromophores. The blue-tinted ice giants, Uranus and Neptune, are much colder and covered in methane ice clouds. So when we start talking about the giant planets, we can, of course, take a look at their composition and see some similarities here. The giant planets hold most of the mass in our planetary system if we are looking at objects apart from that of our own sun. Of course, the sun has most of the mass, but when we look at the planets and the other objects that are here, the giants are going to have most of that. Jupiter alone exceeds the mass of all the other planets combined. Now, the material available to build these planets can be divided into three classes by what they are made of: gases, ices, and rocks. The gases are primarily hydrogen and helium, the most abundant elements in the universe. The term ices means compounds that form from the next most available abundant elements. So that'd be oxygen, carbon, and nitrogen. Common ices, therefore, are water, methane, and ammonia, but ices may also include carbon monoxide, carbon dioxide, and others. Now, when we refer to rocks, this is even less abundant than ices and includes everything else, so things like magnesium, silicon, iron, and so on. So let's look at some of these gases in the outer solar system. In the outer solar system, gases dominate the two largest planets, Jupiter and Saturn, hence their nickname, gas giants. Uranus and Neptune are sometimes referred to as ice giants because their interiors contain far more of the ice component than their larger cousins. Now, the chemistry for all four giant planet atmospheres is, of course, dominated by hydrogen. The compounds detected in the atmosphere of the giant planets are mostly hydrogen-based gases such as methane and ammonia, or more complex hydrocarbons such as ethane and acetylene. Now, there are challenges to exploring the outer solar system. You might already start be thinking about some of these challenges if you were trying to map out the distance between them. So, one of those challenges, of course, is that things are just very far away from Earth. If you look at the flight times when you were to send, let's say, a satellite, or you're like, I'm going to send a deep space probe out there. Well, the flight times are measured in typically things like years or decades if they were to travel out from Earth. Even if things were moving at the speed of light, messages would take hours to pass between Earth and that spacecraft. Now, spacecraft to the outer solar system therefore have to be highly reliable and capable of a greater degree of independence and autonomy, because you can't make a quick instant change to it because of the long time it's simply going to take to send and receive the communication. Now, all our solar system missions also must carry their own power sources, because even though the sun is present, it is too far away really to provide enough energy into things such as solar cells. And even if you did have solar cells, you're going to need a very large array to really capture that solar energy. Additionally, heaters are required to keep instruments at proper operating temperatures, and spacecraft must have radio transmitters that are powerful enough to send their data to receivers on a distant Earth. Because again, we're looking at a very large distance between wherever that probe is and back to the receiving stations on Earth. Now, when we do talk about the exploration of the outer solar system, the first spacecraft to investigate past Mars were none other than the NASA Pioneers 10 and 11 as pathfinders to Jupiter. One of their main objectives was to determine whether a spacecraft could navigate through the asteroid belt without getting destroyed, because at that point, we didn't know the density of the asteroid belt. Was it going to be so packed that something would be destroyed, or was there enough room for something to be able to navigate through easily? Another objective was to measure the radiation hazards in the magnetosphere of Jupiter. Now, Voyagers 1 and 2 carried out 11 scientific instruments, including cameras, spectrometers, and devices to measure the characteristics of the planetary magnospheres. Voyager 1 reached Jupiter and used a gravity assist to help take it on to Saturn, whereas Voyager 2 arrived at Jupiter 4 months later, but then followed a different path to visit all the outer planets. Now, both Voyagers continued onward to explore the outermost regions of our solar system. Now, of course, we also had some other orbiters. We had Galileo, Cassini, and Juno. The Pioneer and Voyager missions were nothing more than flybys of the giant planets, so more detailed studies of these worlds were required. When we wanted to look at Jupiter and Saturn, well, we sent the orbiters that were Galileo, Cassini, and Juno. Now, to date, no orbiter missions have been started for Uranus and Neptune, although planetary scientists have expressed interest in further study of these two giants. So let's start first with the Galileo spacecraft and its mission. The Galileo spacecraft was launched for Jupiter in 1989 and arrived in 1995. Galileo begins investigations by deploying an entry probe into Jupiter for the first direct studies of the planet's outer atmospheric layers. The data from the probe instruments were relayed to Earth via the main Galileo spacecraft. After the probe was vaporized in Jupiter's atmosphere, the main spacecraft was captured into orbit around the planet, where its primary objective was studying Jupiter's large moons. With the Cassini spacecraft, its mission was not Jupiter, but Saturn, and it was another twofold approach. First, Cassini went into orbit around Saturn, beginning extensive studies of its rings and moons, as well as the planet itself. And then in January 2005, Cassini deployed an entry probe into the atmosphere of Saturn's large moon Titan, where it successfully landed on the surface. And with the Juno spacecraft, its objective was studying the Jovian magnetosphere. Its orbit takes the craft over Jupiter's poles, giving us remarkable close-ups of the polar regions, because up to this point, most of the spacecraft had kind of more just explored more near the equatorial region. Juno was originally designed without a camera, but fortunately science added a simple downward-looking color camera to use during close passes by Jupiter. And recognizing the value of such images, both scientific and artistic, it was decided to post the raw images and encourage citizen scientists to process them, which of course has led to some very remarkable pictures of Jupiter.